Hi, welcome back to My Smart Learning. This is a lesson for Year 12s. We're looking at the second part of transpiration, factors affecting transpiration. So it's A-level biology. So if you're one of the students doing the GCSEs, you don't need to watch this one. This is for Year 12s. For Joe, welcome back to My Smart Learning. And I know Joe likes his joke of the day to start my lessons with. So let's see, Joe, you can still send me your jokes on YouTube, on my YouTube channel. They do make me chuckle, but I do always compare them to Alexa's jokes to make sure that you're not been stealing them, you know, the copyright of Alexa's joke. Alexa, tell us a joke.
What does a clock do when it's hungry? It goes back 4 seconds.
Oh dear. Okay, right, so let's get the lesson started, I think. Transpiration then. Factors affecting transpiration. How can transpiration change its speed? How can we make transpiration faster or slower? That's what we're focusing on today. Now, we did do this a few weeks back when we looked at chapter 6, but this actually links better with what we did yesterday on how transpiration occurs. So quick recall quiz, I like to call it high five. You get them all right, all 5 correct, you get a virtual high five from me. So number 1, water enters the roots via what process? So how does water enter the roots? Write it down, pause the video, write them down. These might take a little longer than usual, they're not one-word answers. Question 2, what are the 2 pathways that water can transfer through the cortex? Now remember, when it gets to the root hair cells, through the epidermis, the epidermal layer, then it goes into the middle section called the cortex. Now what 2 pathways can that water take? Question 3, what is the name of that impermeable barrier in the endodermis, the endodermal layer, that one sort of on the inner bit, just before we get to the xylem? Question 4, what is the theory known as of how water moves up the stem to the xylem? So what's the theory? What is the theory of how water moves up the stem? And question 5, those hollow tubes, I think I've already mentioned them. What are those hollow tubes called that go through the roots up the stem and into the leaves? And what's the chemical that strengthens them so they become rigid and don't collapse? So have a go at answering those questions, write them down, pause the video to give you a bit of time, and once you unpause it and restart the video, we'll go through the answers now. So, the answer to question 1, water enters the roots via osmosis. So it's osmosis because, but what allows that to happen, remember from yesterday's lesson on transpiration, the active transport of mineral ions using ATP pumps in minerals into the roots, lowering the water potential. Therefore, the outside of the roots in the soil has a higher water potential compared to the inside. So water moves in via osmosis, which is a passive process. Remember, you can't pump water. Water can't be pushed anywhere. So the 2 pathways then, once it's inside the cortex and the roots, it goes via the apoplastic pathway. The apoplastic pathway, also known as the cell wall pathway, And the second pathway is the symplastic pathway. That's also known as the cytoplasmic pathway. The impermeable barrier, once it gets to the endodermis, there in the apoplastic pathway has to stop because the water diverges. It has to enter the symplastic pathway into the cytoplasm because there is an impermeable, impenetrable barrier. And that's known as the Casparian strip. The theory then, question 4, the theory of how water moves up the xylem. The theory is the cohesion tension theory. Remember we talked about the cohesive nature of water because it's got hydrogen bonding between the delta positive, delta negative of the bipolar nature of water. So you get those hydrogen bonds making water stick together, and it also likes to creep up the sides of the xylem. That's the cohesive nature. The tension bit is because that water gets drawn up because of the negative pressure caused in the leaves. So it's called the cohesion tension theory. So you need to be able to explain the processes behind that. That's what we did last lesson. So if you're not sure about that, go back and have a look at yesterday's lesson on transpiration. The last question, question 5, the hollow tubes, they're known as xylem, and what is the chemical that strengthens them? That is known as lignin. Lignin is the chemical. If you got all 5 of those questions right, fantastico. Give yourselves, or I'll give you a virtual high five. You can give yourself a pat on the back. Now, we're looking at the factors that affect how fast this transpiration actually happens. Well, how can we measure it? Well, transpiration, what is transpiration? First, recall, transpiration is the loss of water from a plant via the evaporation from the leaves. So water transfers through the roots, up the stem, and out those leaves. Water can only evaporate from the plant, so the water potential is lower in the surrounding air of the plant. So outside the plant, the water, because the water vapor is coming out, outside the plant, it's got a low water potential compared to inside the plant, because there's more water inside than outside the plant in the leaves. Most transpiration occurs via the leaves, so the majority of it, because you've got those stomata. Okay, so most of the transpiration is via the stomata, those tiny holes where the water evaporates. Now, obviously, water can evaporate other bits; it can just pass out through the cells, but most of it is through the, heat can transfer out my windows, but if I leave the door open, most of the heat will transfer out the open doors. Those stomatas are like open doors. All right. So, how can we measure transpiration first? So, the piece of equipment we use is called a photometer, a photometer. Don't get confused with a potato meter. It's not a potato meter or an alu meter. Okay, a photometer. A photometer is a piece of equipment that, okay, I'll stop laughing at my own jokes. All right, it's a piece of equipment that draws water through this little capillary tube and into those leaves. All right, and if I trap a bubble in there, as the water gets drawn through these leaves, the bubble will move. And I can measure the speed of that bubble. If I get a stopwatch, I can measure the speed of how fast that bubble moves along the scale there. So I can measure the rate of transpiration. So if I cut a plant, and the way you have to do this, you need to set this up under a tub of water. The reason why it has to be underwater is, remember what we talked about yesterday? If you cut into the side of a stem, you might trap a bubble into there and it will stop the transpiration pull, because you've got an airlock, a little bubble in there. That water needs to be a continuous column. That's the phrase, the continuous column of water. If you cut into it, you got an air bubble trapped. It's not going to pull it up. So you get your plant underwater. It's really fiddly. What you need to do is you need to cut it at an angle underwater. So you still have a continuous column of water. And then you set this piece of equipment, the photometer, under the water. So you have a continuous column of water with the water inside the xylem in that plant. So you cut it, you make sure you got a plastic tubing there or some Vaseline, or make sure it's all completely sealed. You don't want any air entering the system. You don't want any bubbles entering the system. When you set it up though, you've got to make sure that all the seals are tight. But once I've got it set up with a beaker of water, I've got to make sure that I'm going to get one bubble set up in that system. I've got my little, what it says, graduated scale. It's basically a ruler. So the meniscus then, so you can have the end of the water there and the water will draw along. And if you have the water died, you can see it more clearly, but obviously if you've just got water, that's fine. The water will draw along and you can just measure it from that meniscus and how quickly it moves along that scale. Or you can set it up so that you've got a bubble set up in there and that bubble moves along. Now you can have the scale either way around. You can have it's got ones on this side and whatever numbers on that side, or you can have the 0 and the 1 on this side, and it's probably easier to measure going that way. But it's very straightforward. You're just measuring how far the water travels over a given period of time. So you can measure the time. It could be 30 minutes, it could be 1 hour. It will take a while. Water doesn't just it's not like sucking up water through a straw. It doesn't just zip through there like a rate of reaction kind of practical, or rate of photosynthesis practical. It tends to move very gradually over time. So you could run it for about half an hour or up to an hour. And so you can measure how far the bubble moves in an hour, and that'll be your rate of transpiration. So the thing is though, so this meniscus is going to move as the water evaporates from there. Now, is that telling me the amount of water is all of that water evaporating throughout of my plant? Is all of it going? Well, the answer is no, not all of it is being evaporated. It's not 100%. So if I read, I don't know, it goes from 12 and it goes to 6, then it means it's transferred 6 centimeters, let's say, and convert that into millimeters, 60 millimeters in an hour. So you could say, oh, 60 millimeters per hour, or 6 centimeters per hour. Now, does that tell you the amount of water? Well, if I wanted to measure the actual volume of water that's gone through that plant, how would I calculate the actual volume of water per hour? Well, I've only just given you the length it's travelled. If you want to know the actual volume, well, what shape is the capillary tube? The shape of the capillary tube, it's a cylinder. And if it's a cylinder, thinking back to your GCSE maths, how do you work out the volume of a cylinder? The volume of a cylinder, you can measure any prism by the surface area multiplied by the distance it moves, or the length of it. So the surface area though, the shape of the capillary tube is a circle. So the area of a circle, if you remember from GCSE maths, is pi r squared. So pi times the radius squared, that gives you the area of the cylinder. And then if you measure the volume, you times it by the distance it's moved, or the length it's moved. So if it's moved 6 centimeters, you times it by 6. If you want to convert it into millimeters, you'll make that into 60 millimeters. So your volume will be either in millimeters cubed, or which is probably the best number to use, or it could be centimeters cubed. But to make it more accurate, you'd use 60 millimeters. You'll get your answer in millimeters cubed. Now, for instance, let's say 60 times, I don't know, let's say that was 10, let's say 60 millimeters cubed. Is all of that 60 millimeters cubed, has all of that water evaporated? Well, the answer is no, because not all of, remember we talked about necessary evil last time? About 95% of that water is going to be lost or more. So, because some of that water is actually being used by the plant. Some of that water is being used for the cells to become turgid. Some of that water is being used for photosynthesis. So not all of that water is actually transpiring and going all the way through, but the vast majority of it is. So this piece of equipment, this photometer, measures the rate of transpiration. Now what I can do, so as you can see, the water gets pulled up through there and you can measure the distance it's moved. So that's the volume. If I measure the surface area times the length, pi r squared times the length will give me the volume. And I do it over a certain amount of time, and that'll give me the volume per hour or per minute, or whatever calculation you want to do. But what's the point? The point is to find out how factors can affect how quickly the water evaporates through. So what can I change? What can be my independent variable? What kinds of things can I see, the factors that affect the rate of transpiration? Well, you could change the light intensity. So I can have maybe one lamp shining on it, then 2 lamps, 3 lamps, 4 lamps, or have one lamp and change the voltage on the power pack to change the brightness of the bulb. You can have the lamp close and then move it further away. So you can change the light intensity and see how that affects the transpiration rate, how fast that bulb moves. You could also change the temperature, so you can have it varying temperatures in the room to see how that affects the rate of transpiration. You could measure how wind speed affects the rate of transpiration. Now, if you're just going in wind speed, you can just get a fan, switch the fan on, have it blowing. You can have it close to it, further away, or you can have it on your fan. You can have different settings like 1, 2, 3 to change the wind speed to see how that affects the rate of transpiration. A trickier one to do is measuring how humidity affects the rate of transpiration. Now, to do that, you'd have to actually get a bag of water vapor and sort of wrap it around in a sealed bag so that it's in a bag of moisture, and see how that affects the rate of transpiration. That's a bit tricky to do. So what are the limitations of this particular piece of equipment? It measures the water uptake, but it doesn't tell you how much is transpiring and how much is actually being used. You don't know that. You just know how quickly that water is going up. Cutting the plant shoot may damage the plant. Okay, so obviously it's going to be the end of that plant's usefulness. Plants have no roots, so no resistance to water being pulled up. Now, this plant doesn't have any roots. Usually, if we're trying to measure the rate of transpiration, if you want to do it compared to what a real plant's doing, well, the real plant's going to be in the soil. So if it's under the soil, then the water's being drawn through the roots, and therefore there's going to be some resistance there. it's not going to be pulling it up as fast as it is here because it's got no resistance here, because there's no roots, you cut them off. So, key factors then. These are the 4 main factors that affect the rate of transpiration. So you need to know the factors and the explanation behind them and why it causes the rate of transpiration to change. Humidity is the odd one out of the 4. So we'll start off with that one. The other 4 increase it. Humidity is the one that actually decreases it. So if I increase humidity, if it's more humid on the outside, then the transpiration decreases. Why? Well, what is humidity? Humidity is the saturation of water. How much water vapor is there in the air? So if you think of a tropical rainforest, it's got very high humidity. So if you're in a tropical rainforest, the transpiration rate will be, because of the humidity, will be reduced. But obviously in tropical rainforest, it's really hot and sunny, so obviously that's going to increase it. So that's why it's always very sticky and clammy in a rainforest. But what does humidity do? It actually slows down the rate of transpiration. Well, think of it like this. Imagine you're washing your clothes and you put them out on a washing line outside in the garden. If the day is very wet and damp, are your clothes going to dry faster? Well, no, because there's a lot of moisture in the air. So same thing here. If you've got water potential inside the leaf, the water potential outside the leaf, if it's a humid day, the water potential is going to be high. Now, you want to make it go faster, you want to make sure that you've got a very big difference in water potential gradient. So you want to be very high on the inside of the leaf and very low outside the leaf. That would cause transpiration to occur faster. Now obviously a plant doesn't want to do that because that's bad news for the plant, because the plant will be losing water. So plants that are adaptive, which we'll come into in a second, try and reduce transpiration. Okay, so that's what they want to do. Now, these things will increase transpiration, but reducing humidity will increase transpiration. Why? Because if you lower the humidity, there's going to be a low water potential on the outside, high on the inside, so therefore the water potential gradient is steeper, it'll come out. If you make it more humid, that means the water potential on the outside is higher, and it's high on the inside. That gradient, that slope isn't as steep, it's not going to be coming out as fast. I use the analogy when I talk about diffusion, when we talk about Fick's law and things, about these gradients. What do I mean by this gradient? Well, think about a slope, all right? If you get some marbles and you drop it down a slope and the slope is very shallow because the gradient difference isn't very big, those marbles will go rolling down slowly. But if I make the slope really steep, okay, and let those marbles go, they're going to go bumming down there. So if you've got somewhere where it's very, very high and somewhere where it's very, very low, the steeper it is, the difference in the steepness, the gradient, the faster the stuff will go bumming down. Now I know in my lessons I've talked about a fat bloke on some roller skates, still makes the same sense, right? So if you nudge a guy on his roller skates and it's shallow, he's not going to go down very, very quick. But if you nudge a guy and he's on a steep slope, he's going to go bumming down really, really quickly. So what are the other 3 things? Wind. If you make it more windy, if the wind speed is increased, why does that make the transpiration faster? Well, wind speed will blow that water vapor away from outside of the leaf. And if it does that, it's moving the water molecules away. That means it's lowering the water potential outside. Inside's always going to be higher, therefore it's going to come out much, much faster. That one's an easier one to understand. Just blow it away, lower the water potential. Temperature then. If it gets hotter, that means the higher the temperature, the more kinetic energy the water molecules will have. And if they've got more kinetic energy, they're going to evaporate away faster from outside the leaf. Which means if they evaporate faster from outside the leaf, it's going to lower the water potential outside the leaf. Inside the leaf is going to be much higher water potential, so water will evaporate out much faster and diffuse out much faster. So it's going to increase the rate of transpiration. Light intensity then, the brighter the light, well, generally speaking, if there's more light about, usually, not all the time though, usually there's going to be much, much more energy for the particles. And therefore, the water particles will gain more kinetic energy and they'll move away faster, and therefore you're going to have a lower water potential on the outside, higher on the inside, and water will diffuse out much faster. So you need to know the 4 key factors that affect the rate of transpiration. And now we need to look at we need to know the 4, but there's also some more as well. There's 6, because we've talked about the 4 major ones, and then there's 2 others. So we talked about relative humidity, why that causes it. We talked about the air movement, which is the wind speed, and we've talked about the temperature. You've also got atmospheric pressure. So atmospheric pressure then, what that will do is, if you decrease the atmospheric pressure, it increases the rate of transpiration. Why? Because if there's low pressure on the outside, that means there's less water there, because there's low pressure. So water molecules will come out much faster, because you've got to have a higher water potential to a low water potential. Okay? So, because if you've got a higher pressure outside, that's going to be harder for the water vapor to go against that pressure gradient. You want to have a difference in pressure gradient. So the more water molecules there are, the higher the pressure. So if there's less water molecules outside, there's going to be lower pressure on the outside. So water, that gradient's going to be steeper, so it's going to come out quicker. Water supply, obviously, the more water you've got, the faster it will transpire. So transpiration rate is lower if there's little water. If there's not much water about, you're not going to it's not going to get pulled up as fast, is it? So if you've got a dry day, water's not going to be transpiring out as fast. Light intensity we talked about as well. The greater the light intensity, the greater the rate of transpiration, because photosynthesis is going to be faster as well. And photosynthesis is faster, the stomata are going to be opened. If the stomata are opened, more water is going to evaporate out. Obviously, if it's darker, the stomata is going to close because there's no photosynthesis going on. Therefore, it's going to reduce the rate of transpiration. So, those are your reasons. Now, what other factors are going to affect the rate of transpiration? So, the leaf size. If you've got much flatter and larger leaves, you're going to have more surface exposed to the external environment, therefore more space for the water to evaporate out. The thickness, this all goes back to Fick's law. Remember, the rate of diffusion is proportional to the surface area times the concentration gradient divided by the length of the diffusion pathway. And that length of diffusion pathway is basically its thickness. So if you've got the surface area, the flatter, the bigger, the more space you've got for the water to evaporate. The thickness then is, if you've got a waxy thick layer, it's going to be harder for that water to evaporate, so it's going to make it much more difficult for transpiration to occur. Stomatal frequency, that basically just means how many stomata are there. So if you've got loads of stomata on your underside of your leaf, the more stomata you have, the more transpiration will occur, because you've got more holes, more open doors for the water to evaporate out. Stomatal size, obviously if you've got tiny stomata, there's the door's smaller, less water is going to evaporate out. If the stomata are much bigger and larger, more water will evaporate out. And you've also got stomatal position. What position are the stomata in? If they're in a position where it's more exposed, like to the air, more water will evaporate out. If you're going to see, we're going to look at some xerophytes in a minute. If you've got stomata sort of curled inwards inside a leaf, for instance, the position of it is going to cause the water vapor to stay in a certain bit. Therefore, it's going to reduce the water vapor, transpiring out. So, effect of wind speed then, we talked about that. The greater the wind speed, the faster the rate of transpiration. And also the size of the diameter of the stomata, the faster the rate of transpiration. So if you've got moving air, it's going to be much faster compared to if you've got still air. So the larger the diameter, the faster the rate of transpiration. But obviously once it gets to a particular point, it doesn't make that much more difference. It starts to flatten out, it starts to plateau. In still air, closing the stomata is less effective in controlling the transpiration rate, because obviously it's not going to be coming out. So what happens in still air? In still air, that's the air movement, showing you there's not much air movement. Okay, the air water outside accumulates, the water vapor accumulates on the outside and it becomes saturated. So therefore, there's a high water potential outside compared to inside. Therefore, the water potential gradient isn't as steep, so not much water is going to evaporate out. If you've got moving air though, what you're going to do is you're going to blow that water vapor away from the surface, and if you do that, you've now got a very low water potential on the outside and a high water potential on the inside. So water, so you've got a low water potential here, there's a bigger, steeper gradient of the water potential gradient, therefore it's going to diffuse much faster out and transpire out quicker. So you've got these little diffusion shells here showing you that if you want water vapor to transpire out, you don't want these shells. If you blow these shells away, it'll come out much faster. Okay, water will diffuse out. So the frequency, if you've got the loads of stomata close to each other, small stomata close to each other, you can make these little shells, so this kind of boundary of sort of water vapor, and therefore it's making it harder for the water vapor to diffuse out. Okay, so let's have a look at some plant adaptations. What is wilting? Well, wilting is where leaves start to lose lots of water and they become all floppy and what we call flaccid. The word flaccid means floppy, they become wilted, because the water will come out of the vacuoles, those permanent vacuoles, and they'll draw out, and then the plant will die, because if they're not turgid, which is the opposite of flaccid, they won't face the sun, they won't get as much sunlight for photosynthesis. So, a quick reminder of our leaf structure. So we got our guard cells there, and you got the stomata opening and water coming out of it, and there's your stomata closing. Why do they open and close? It's to do with during the day when the sun comes up, as the sun rises, they're flaccid there if water doesn't go into them. Water draws out of them, they become flaccid and they close, because the inner lining is thicker, the outer wall is much thinner, the stomata is closed there. And when they become turgid, when there's water going into them, they become turgid, and because they're sort of like two bananas facing each other, because one side is thicker compared to the outer layer which is thinner, they start to bulge and make that shape so that there's a hole, a stoma, in the guard cells, between the guard cells, so the water would evaporate out. Why do they become like this? It's to do with potassium ions. Active transport. When the sun comes up, there's more active transport. Potassium ions will be actively transported into those guard cells, lowering the water potential. Therefore, water will go from the epidermal cells surrounding these guard cells. The potassium will pump from those cells into the guard cells. Therefore, water from those endodermal cells, or sorry, epidermal cells, they will move into the guard cells by osmosis, making them more turgid. Okay, so potassium ions get actively transported into those guard cells, lowering the water potential by doing that, and therefore it's lowering the water potential. Water will move into those guard cells and they will become turgid because they move down the water potential gradient. Therefore they become turgid and the stoma opens. So water will escape. Xerophytes then. Xerophytes, what are they? Xerophytic plants. These are special plants that have unique or special adaptations that limit and reduce the rate of transpiration. Your classic example of that is the cactus. Okay, the cactus. Living in conditions that are very harsh, where there's limited water, they don't want to lose that water that's going through them. They want to keep as much of that water as possible. So what kind of adaptations do they have? So for instance, a cactus then, what you might want to quickly draw a cactus and pause the video and try to annotate as many different adaptations you think a cactus has to reduce its water loss. So if you want to do that now, pause the video and then we'll restart now. So what does a cactus have? Well, cacti don't have leaves. A cactus has these little spines here, and these spines are the equivalent of these leaves, but a leaf is broad and flat, so it's got a large surface area, so water can evaporate and go out. Whereas a cactus is got these little spines, and therefore there's no surface there for the water to evaporate from. So they've also got fleshy stems, some of these xerophytic plants. We call them succulents. A succulent is a plant that's got fleshy stems, like the aloe vera there, and the cactus there. That's why animals will want to come along, like let's say a camel, and they want to take, there's no water around, so there's no way for them to drink water. So to get their water in their diet, because obviously they need to be hydrated, they'll take a bite out of these plants to get their water content. But how would you take a bite out of a cactus? I think not. They're very spiky and they'll damage your mouth. Whereas the camel's adaptations in its mouth is toughened mouth, so you can take a big munch out of those. Okay. So also they've got, like some of these have got silver surfaces to reflect some of that sunlight away, and by doing that it's reducing the heating effect, so it's not warming them up too much, so they're not going to evaporate more water, and also the heat can damage the enzymes if it gets too hot. So what else do they have? They have a thick waxy cuticle. Okay, therefore you've got a larger diffusion pathway, a thicker, a longer diffusion pathway. It's waterproof. It's not to stop water from coming in, it's to prevent from water from evaporating from inside to outside. Reduced leaf areas, for instance here we've got needles. Some plants have hairy leaves. If you look at in the classroom, we've got those geraniums. If you go and feel the leaf of a geranium, they feel quite furry. And the hairy leaves, what they do is they trap a layer, it's that whole boundary idea, they trap a layer of moisture, of water vapor along the leaf, and by doing that it raises the water potential outside the leaf compared to the inside, and therefore reducing the water potential gradient, therefore reducing the transpiration. You've got sunken stomata in some plants where the stomata are not in level with the epidermis on the lower side, they're actually sunken deeper in there, so you get these what we call pits or grooves. These pits and grooves, what happens is the water vapor evaporates out, it gets trapped in that little pit or that groove, so therefore when the wind blows it doesn't blow it away because it's stuck in that pit, and therefore compared to inside and technically outside that leaf from the air spaces in the spongy mesophyll layer, there is a lower gradient in that water potential gradient, therefore water doesn't evaporate out as fast. You've also got rolled leaves. I'll show you an example of that on the next couple of slides or so, where the leaves are rolled inwards, and by them rolling inwards, like marram grass that you find on the beach and stuff, if it rolls inwards, the stomata might be there on the flat side, but if they're rolled inwards, the stomata are all facing inwards inside that leaf in the grasses, and then the water vapor diffuses out and gets trapped in the inside, therefore keeping the water potential high compared to inside the leaves, so water vapor doesn't want to or can't evaporate out as fast, so it can't transpire as fast. So increasing the water vapor around the stomata reduces the water potential gradient, so slows the water loss. It reduces transpiration. That is the key phrase that you might want to write down. Okay, it's all of these adaptations are based around that. So here's some more notes on that. I will post this on Show My Homework, so you've got the notes to make down in your notes. And make sure you answer the questions in the Caboodle textbook based on this. And we're going to have a go at some exam questions on this as well to have a go at. So we've covered all of those. We talked about sunken stomata, thickened cuticle, waxy layer. We've got the hairy leaves. Also the shape, size and the arrangement of the leaves will also affect it, and also the stomata too, how many stomata. So that's the cross section of a marram grass that I was just talking about. There's the leaves are rolled inwards on themselves so that the stomata are inside. So you got your sunken stomata there. The hairs also within inside the marram grass as well, they'll trap water vapor, so you get like a layer of moisture of water in there. The water vapor as well will get trapped in that little space, and that's going to reduce the water potential gradient. Adaptations, then we talked about of these xerophytes. Think about your cactus, got deep extensive roots so they can get as much water as possible, maximize water uptake. They've also got shallow roots that sort of stem outwards so that when it rains, because water's not going to go very far deep into the sand most likely, so then you can get this water as much as possible. They also have pump in lots and lots of solutes into the roots, so they go very, very salty inside the roots. Why? Because it's going to lower the water potential, so making that gradient as big as possible, water will diffuse by osmosis into those roots. We talked about some of the shallow roots as well, so they can absorb some of the condensation that happens on top of the sand or the soil in the morning, so they can absorb some of that water from the moisture that's in the air, in the humidity of the air. Think about the desert, it's going to be very hot during the night, during the day, sorry, and during the night it gets very, very cold, and that water vapor that's in the air condenses and becomes like dew on the grass or on the sand in the morning. If they've got shallow roots, they can get some of that water. So over the day then, during the night then, middle of the night, stomata are closed. Why do the stomata start to open, hitting a peak around lunchtime, and then start to close during the evening, and they're all pretty much closed at night? Why do we have that shape? Well, during the dawn, they start to open. The sun is rising. Sun is rising, stomata start to open. During the night, they're closed, obviously. There's no photosynthesis, there's no sunlight. What's the point? You'll be losing water. Complete waste of time. So they start to open, hitting a peak around lunchtime, because that's the highest point the sun is at. So the light intensity is at the greatest during the middle of the day. It should be the warmest part of the day around then as well, because the sun's been up the longest. It's the highest point. The day should be warming up. Therefore, transpiration will be getting faster as well. And then during the afternoon, the sun starts to set, and therefore the stomata start to close. Now, some plants close stomata during the hottest time of the day just to conserve water, because that's the point at which they will lose most water, because that's going to be you'll get a line usually the similar kind of shape for transpiration, because that's the rate of transpiration as well when the stomata are opened. Okay, so some plants have special adaptations where they will actually try to close it during the peak time of the day to reduce their water loss during the hottest, peakest part of the day. It's a bit like in the Mediterranean, people like to go for I was going to say fiesta. Fiesta's a party, not a fiesta, a siesta. They go for a little nap during the middle of the day because it's really, really hot. There's a phrase, mad dogs and Englishmen go out in the midday sun. Why? Because mad dogs and English people, they like to go out sunbathe when the sun's at the hottest part of the day, which is the stupidest time to go because you'll get sunburn and get skin cancer. Whereas all the locals, they'll go indoors and have a little sleep, a little power nap, because it's hot, might as well get some rest, and then you can go out in the evening and enjoy yourself. Whereas the Brits will be there nursing their sunbathes with some after sun. So yeah, the hottest part of the day. So some plants are actually adapted to close their stomata during that time. So what does stomata look like over the time? You can see stomata o'clock. So you can see the shapes that they're making during the different times of the day. So here's some exam questions. 4 questions for you to have a go at. You might want to press pause, have a go at those 4 questions, and we will go through the answers one by one after these. So, but I will post this and show my homework for you to have a go at. So question 1, what is transpiration? And give 3 environmental factors which will increase transpiration rate. That's question 1. Question 2, explain how potassium ions are moved into the guard cells in light and how this affects the guard cells and stomata. A 6-mark question. Question 3, give 3 adaptations of xerophytes may have to reduce transpiration and explain how they do this. That's 4 marks. And question 4, plants close their stomata at night and some also close their stomata around midday. Explain why this is advantageous to the plant. That's 2 marks. Pause the video, have a go at those questions. It should take you, what, let's say 8, 12, 14, 15 minutes or so. So if you have a go at that, this is about an hour lesson. So pause the video, this should take you about 10 to 15 minutes to answer those questions. And once you've had a go at those, I will restart the video now and we'll go through those answers. Now those guys in my year 12 class that are watching these, I'm going to post this video to you so you've got the questions there and the mark scheme after on Show My Homework. For the rest of you guys who are watching around the world, thank you for watching and subscribing to these videos. I really appreciate it. I'm happy that I'm getting to help not just my year 12s and my GCSE classes as well, along with my A-level classes. At this time when everyone's locked indoors, it's nice for the fact that I can help people learn their science and their biology from home, but also there's people watching around the world. So much appreciated. Make sure you keep liking the videos obviously and subscribing and sharing it so other people can use it. But I'll sort of quickly go through the answers and then yeah, please send me messages. It's nice to hear from you guys on the YouTube channel. If you've got any comments, please make them and I'll make sure I reply to you. So the answer then to question 1. So the answer to question 1 for 2 marks. Transpiration is the loss of water from a plant by evaporation. And the 3 factors that increase it is higher temperature, higher wind speed or increased air movement, and lower humidity. They're the 3 things that increase it. Also greater light intensity, you could have said as well. So greater light intensity will increase it. lower humidity. So there's one more thing you could have said there. Question 2 then, there's a 6-mark question, is all about the potassium ions. What do they do? Well, potassium ions are pumped into the guard cells by active transport, 1 mark, against the concentration gradient, because it is active transport, so it goes against the concentration gradient, going from a low to high concentration. This lowers the water potential inside the guard cells, so therefore water is drawn into the guard cells by osmosis, because it goes from a high water potential to a low water potential. From the surrounding cells, from a higher water potential to lower water potential. The guard cells then swell up and become turgid, so they start to bend and make that sort of those C shapes, causing the stomata to open. Question 3, 3 things that you have to say, I think it was for the adaptations of xerophytes. You've got thick waxy cuticle, reduces evaporation because it's much thicker, longer diffusion pathway. Curled leaves we've got, that trap is water and moisture inside the curled leaf. Reducing surface area by having spines instead of having leaves. Hairy leaves, remember, traps a thin layer of moisture on the surface of the leaf. And sunken stomata as well. You've got these pits and these grooves where the moisture gets trapped inside that pit. That increases or maintains the high water potential, so it lowers that water potential gradient. That's where most of that marks are. It's all to do with that water potential gradient. And the last question, stomata closed at night when there is low light for photosynthesis, so reducing water loss by evaporation, the transpiration by the stomata. Closing the stomata at midday, which some of these plants do, there's special adaptations, which is the hottest part of the day, is an advantage in hot, dry countries because you're reducing the transpiration, so you're reducing the amount of water lost at the peak part of the day. So, any synoptic links from other topics? Water potential, definitely. Osmosis. We've got active transport mentioned. Respiration, we're talking about active transport there. Photosynthesis we mentioned, because when stomata have to open. So, I hope this has been useful for you guys, looking at the rate of transpiration and the factors affecting it, and how the photometer works. Please make sure you're watching the videos on My Smart Learning. Tomorrow, Year 12s, we're going to go on to translocation. In your caboodle textbook, it is actually 2 pages. But what I'd like you to do is make sure you read up on it beforehand. Make sure you get your notes. I'd like you to watch the video tomorrow. I'll put it on Show My Homework on translocation. I will try to double up the lesson into 1, which should be possible. It'll probably be a slightly longer video. And thanks for watching. Keep watching the videos, like the videos, subscribe if you haven't all done so already. I really appreciate it, thank you, and share it. So look after yourselves and take care, and I'll see you guys tomorrow. Bye.